So now that we are familiar with the concepts of budget sets, indifference curves, utility functions, choice under uncertainty, tangency condition, and so on, let us actually go back and look at the problem that we studied last week, which is choice under uncertainty. So notice the logical set of steps that we kind of like took when we first started thinking about utility functions this week. So initially we thought of utility functions as defined over two commodities or goods. So think about juices and chocolates and so on. Then we saw that when we are considering intertemporal choice, we can treat these two commodities, one and two, as commodities at different dates, right? So then we had a choice of consuming today, which is consuming in period one, versus consuming in the future, which is consuming in period two, right? So instead of thinking of two different goods, now we are thinking of consumption at two different dates as two different commodities. Now, when we are discussing choice under uncertainty, we go even one more step beyond and we start thinking of these two commodities as commodities or under different situations, right? So these are what are known as contingent commodities. So basically think of two events, A and B, that can happen. Then we are going to define one contingent commodity as consumption if event A happens, and another contingent commodity as consumption if event B happens. This is in the same line that we have been thinking of, right? Where we were thinking of utility of over two commodities or utility over consumption at different points. Now we are thinking over utility over consumption under different situations playing out, right? So in the context of the insurance example that we had discussed last week, the two events were if the accident happened, what would be the consumption, and if the accident didn't happen, what would be the consumption. So these were the two contingent commodities, and then we had defined a utility function over that, right? So again, if we now kind of like retrace the different concepts that we had studied, so first we need to think about what are the choices that are available. So we discussed budget constraint, which we called state contingent budget constraint, that specifies the set of contingent commodity bundles that a consumer can afford in different cases, right? Where different events happen. Then the notion of preferred alternative, we actually again need to discuss what are the consumer's preferences over the different contingent commodities, right? And so therefore we described it in terms of thinking about different preferences over, if you think about it, it's about preferences over probability distributions. And so therefore think of those probability distributions as gambles or lotteries. So the question is, what is the consumer's willingness to take such lotteries, right? And how much is he willing to pay to avoid those uncertain situations, right? So that will typically be determined about how the consumer thinks about the various combinations of contingent commodities that are available. And importantly, it also then starts depending on what are the probabilities of the different contingencies happening, right? So in this context, we introduced the expected utility form, or so what is that is basically an assumption that we are making that the utility function takes a particular form. So what is the expected utility function that we studied last week? So imagine that there are two events, 1 and 2, that can happen with probabilities pi1 and pi2 respectively. And if the contingent consumptions are C1 if event 1 happens and C2 if event 2 happens, then the utility function under expected utility has this particular functional form, right? Where it's the weighted average of the utility of the consumption in the two different states, where the weights are the probability of the two states happening. So this is how we are going to be thinking about preferences in presence of uncertainty. Okay. And finally, if we want to put this all together, remember the last part is that somebody has to choose the most preferred alternative from those available. So basically it comes down to maximizing this utility subject to the state contingent budget constraint, right? So that is the overall structure. So let us now look at several problems just to see how this actually works in practice. So imagine that you have Samsung, who owns a factory which is located near a river that occasionally floods. So Samsung is planning to sell the factory next year and retire. However, the income that he is going to get depends on the amount that he can sell his factory for. And the amount that he can sell his factory for depends on whether there is a flood or not, and whether he buys insurance or not. So if there is no flood, then he can sell his factory for 5 lakhs. And if there is a flood, he can only sell it for 50,000. Okay. So this is what would have happened if Samsung does not buy any insurance. However, Samsung also has the choice of buying flood insurance at a cost of 0.1 for each 1 unit worth of coverage. So Samsung also has experience with past occurrences of floods, and he thinks that the probability of a flood occurring in this particular year before he sells the factory is given by 1 by 10. Okay. So first we need to think about what are the different contingent commodities here. So the two events are basically if the flood happens or if the flood does not happen, right? So let's call CF the contingent commodity money that Samsung would have at his disposal if there is a flood. And let's denote by CNF the money that Samsung would have after selling the factory if there is no flood. So we also need a description of the expected utility. So this is given by this expression that you see here. So if you now compare it with the general form that we had discussed previously, so notice that you get pi1 UC1 plus pi2 UC2. So pi1 is the probability of the flood, which is 0.1, right? So that is information that is already given to you. And pi2 here is 0.9, which is the probability of the flood not happening. And the particular UC1 that you see, small UC1, that's given by square root of CF and square root of CNF, right? So that tells you that the small u of x is basically taking the form of square root of x. And as we have studied before, so this is an example of a concave utility function. And so therefore that tells us that Samsung is risk averse, right? Okay, so that is the basic setting. And now we are going to go through a set of steps where we discuss how do we derive the state contingent budget constraint. And we are already given the utility function, then we will think about how to maximize this utility function subject to that state contingent budget constraint. So first, let's go through this set of steps. And this actually mirrors our discussion of the car accident insurance that we studied last week. So in case that was not something clear to you, this is again another opportunity to go over the same concepts. So suppose first that Samsung buys no insurance, then what will his contingent consumption bundle be? So in case he buys no insurance, then basically the amount of money that he is going to get is going to be the same as the information that is given here, right? So if there is a flood, then he is going to get a contingent consumption of 50,000. And if there is no flood, then he is going to get a contingent consumption of 5 lakhs, right? And so we'll note down here that so if he buys no insurance, then in each state, his contingent consumption bundle will be equal to the value of the factory. And this is the value of the factory if there is no insurance and if there is a flood and if there is no flood, right? Okay. Now let's think about the case where he is actually going out and buying insurance. So suppose he buys insurance that pays him X units in case of a flood. So he has to pay an insurance premium of 0.1x. How do we know this? This is based in this information that is given here, that he can buy flood coverage at a cost of 0.10 for each 1 unit of coverage, right? So here we are thinking of not for 1 unit of coverage, but for X units of coverage. So then this is the premium that he has to pay, right? Now, the crucial thing about the premium is that this has to be paid before we know whether there is going to be a flood or not. And hence it has to be paid regardless of whether there is a flood or not, right? So this is a payment that will be deducted from Samsung's amount of money that he has in both the states of the world, because this has to be paid regardless of whether there is a flood or not. Okay. So what happens if he insures? So suppose he insures for X units, then what that means is that if there is a flood, then he is going to get a payout of X units from the insurance company. Okay. And so then the question is that suppose he has actually purchased a contract that pays him X units in the event of a flood, then if there is actually a flood, what will be the amount of money that he'll have? And if he has purchased this insurance, but there is no flood, then what will be the amount of money that he has? So here we just have to systematically think about the two cases. So remember, we are given that what is the value of the factory if there is a flood and if there is not a flood. We are told that he has purchased an insurance coverage of X, and we know that the premium that he has to pay to purchase this insurance coverage, that has to be paid in the both states, but the insurance company only pays out if the bad state happens, which in this case is the flood, right? So let's put this all together. So if there is a flood, then Samsung will be getting this much amount of money. So this 50,000 corresponds to the value of the factory that he is getting when he is able to sell once the flood happens. So that's just 50,000. Then he has to pay the premium regardless of whether there is a flood or not. So we have to deduct this premium that he's paying. So that's 0.1x. And if there is a flood, then of course the insurance company gives him money. So then this is the amount of payout that he receives from the insurance company. So this is the total amount of money that he's going to have, which if you simplify, becomes 50,000 plus 0.9x. Okay. Now, what happens if there is no flood? In this case, the value of the factory that he's going to get is 500,000 or 5 lakhs. He's going to still have to pay the premium. That's the minus 0.1x. But of course, in this case, the insurance company is not going to pay out. So this is the total consumption that he has. Okay. So we notice that the value of the factory is more, but of course, there is no payout also. All right, then can we put all of this together to derive the state contingent budget constraint? So remember, when we are deriving the state contingent budget constraint, what are the two commodities, if you like, this is the consumption if there is a flooding and consumption if there is no flooding, right? So we have almost all the information in part 2 that we had. The only thing is we have this variable x which we want to eliminate, right? So this is very easy to do here because these are linear equations. So for example, this is something in terms of 0.9x, right? And this is something in terms of 0.1x. So you can easily get this by manipulating this expression and eliminating x from these two equations. So if you go ahead and do that, then you end up getting an equation which is of this form, right? 0.1 CF plus 0.9 CNF is equal to 455,000. Notice that, as usual, this is a negatively sloped line. So what that tells you is that if you want to increase consumption in any one particular state, you have to reduce the consumption in the other state, right? Basically, you're transferring money across the different states. So this is the budget constraint. Now, in order to complete the problem, we need to think about what's the optimal choice. And as before, we are going to go through this set of steps where we are going to get basically a pair of equations, one of which will be of the form that the slope of the indifference curve, which is the MRS, is going to be equal to the price ratio that you get from the budget constraint. And then, of course, you also have the budget constraint, right? So we are going to use these two equations to calculate the different things that we care about. So the first step is what is the marginal rate of substitution? So as before, the marginal rate of substitution is the negative of the ratio of the marginal utilities, right? So if here CF, think of that as on the x-axis and CNF on the y-axis, so then the marginal rate of substitution is given by this expression that you see here. And we can calculate the marginal utilities from the utility function here. So that is 0.1 into half multiplied by 1 by square root of CF. And then you also have 0.9 into half multiplied by 1 by square root of CNF, right? So those are the two marginal utilities of the two commodities. And if you put those two here, you end up getting this expression that you see here. Okay, so that's the marginal rate of substitution. Then from the tangency condition, the optimal point is given by the point where the marginal rate of substitution equals the price ratio of the state contingent budget rate equation that you found. So from here, we can see that the slope is given by minus 0.1 by 0.9. And so we can just equate these two slopes. And from there, the 1 by 9s cancel out. And you basically end up with CNF is equal to CF, right? So this is the tangency condition. And finally, in order to actually solve for the optimal point, what we need to do is we need to use the state contingent budget constraint as well, right? So here, if you put in CF equal to CNF, we end up getting that CF is equal to CNF equal to 455,000. Now, usually in most places, this is where things would have stopped in the previous optimization problems that you saw. Here, however, the point is not to calculate what CF and CNF is, but remember the point was to actually figure out how much insurance will Samsung buy and what's the premium that Samsung will pay, right? So how can we use this information? Well, we have already calculated that CF and CNF are 455,000. Now, if you go back to, for example, this equation, where remember X is the amount of insurance coverage that you will buy. So we have CNF is equal to 455,000. So that allows you to actually solve for X, right? So if you use that equation to solve for X, you end up getting that that's going to be equal to 450,000, right? And so therefore, what's the total premium? So that's 0.1 into this amount of insurance coverage. And so therefore, the total premium that Samsung is going to pay is equal to 45,000. So notice one thing also in the solution, that we end up with a situation where you actually have full insurance coverage, right? So CF and CNF is equal to 455,000, right? Now, this isn't so much a surprise. And the reason is because of our theoretical discussion that we had last time, right? So if you actually notice the detail, so here also actually you had insurance which was actually fair, right? Why was the insurance actually fair? Because the probability of the bad state happening, which is 1/10, it was exactly equal to the rate at which you were able to buy insurance premium, right? So this was exactly the case that we had discussed, but not using numbers, but the theoretically when we had discussed last week, when what happens if you have a risk-averse person who is buying deciding how much insurance to buy under actually fair insurance, right? So this was similar to that case. Okay, so that was one question. Let's look at some other questions. So you have got Rishabh, who has a utility function of the form ux equal to square root of x. So again, this tells you that basically Rishabh is a risk-averse person because this utility function is concave, right? Okay, so Rishabh is a promising fast bowler. And as we know, fast bowlers tend to get injured, right? So if he's not injured, he expects to get a contract which is worth 1 million soon for playing cricket professionally. However, if he gets injured, he is going to end up just getting a job which is going to pay him only 10,000, right? So it's a small fraction of what he would have got if he remains injury free. And there is a 10% chance that Rishabh is going to get injured badly enough, which will end his career, right? So first, suppose he does not buy any insurance, what is Rishabh's expected utility? This is the first question. So we can calculate this fairly easily. So we use the functional form that we have discussed before. Remember, this is the expected utility here. The two contingencies, two events are whether he gets injured or not. If he does not buy insurance, if he gets injured, he's going to get only 10,000. But if he does not buy insurance and he does not get injured, then he's going to get 1 million, right? And we can actually put this all information together, and we end up actually getting this expression for expected utility, right? So with 0.1 probability he gets injured, in which case he's going to get 10,000 only. With 0.9 probability he does not get injured, in which case he's getting this much amount. And if you do the calculation, then the expected utility turns out to be 910. Okay. Now here we want to think about insurance, but instead of asking the usual question where the premium rate is given and you derive the state contingent budget constraint and then you solve for the optimal amount of insurance, here we ask a slightly different question, right? So suppose that Rishabh can pay P for an insurance policy, which is such that it would pay him the exact loss that he's going to suffer. So the gap between what he was earning if he was not injured minus what he's earning when he's injured. So the insurance is such that this is going to pay him out exactly this much amount of money. Okay. So if he does purchase this insurance policy, then the good news is that he's always going to get this 1 million amount, right? Because the insurance policy is going to cover the complete loss, right? And of course, he has to pay this premium P regardless of whether he's injured or not. So his consumption in both the states is going to be the same and is going to be equal to this 1 million minus P regardless of whether he's injured or not. The question is, what's the maximum that Rishabh would be willing to pay for this type of insurance policy, right? So in order to find out what's the maximum that he would have to pay, we need to actually look at this equation that is outlined here, right? So let's understand how do we get this equation. So on the right hand side, you see 910. So this is basically the insurance, the expected utility that Rishabh would have got if he had not purchased any insurance. And on the left hand side, you see this 1 million minus P and you take the square root of that. So what is the 1 million minus P? So if he buys the insurance, remember that he's going to get 1 million minus P regardless of whether he gets injured or not, right? And we know that his utility function is ux equal to square root of x. So we can put this 1 million minus P there. So this is his utility if he purchases this insurance policy, right? Now, why must these two things be equal? Well, suppose that this was for strictly less, right? Then clearly Rishabh should not buy this insurance, right? Because if he does not buy this insurance, he's getting a higher expected utility. Suppose this was strictly greater, then in that case, P is not the largest amount that he is willing to pay, right? Because he can then afford to pay a little bit more and still end up with a higher expected utility, right? So only when these two are the equal, right? That's when we actually obtain the highest value of P that Rishabh is willing to pay in order to get this insurance. And hence we can look at this expression and solve for it. And we'll end up getting that P is equal to 1,71,900. Okay, so far we have been looking in terms of insurance by, let us say, private agencies and so on. Well, let's look at an example of an intervention that where governments are actually acting to insure different agents, right? So imagine that you have a collection of investors whose preferences are represented by expected utility function, which is of this form. So from here, again, you notice that we have got x1 to the power half, so square root of x1. So again, we have investors who are risk averse, right? So you have got investors who each of whom are going to place 100 units in a fund, and the manager of this fund has the opportunity to place each of these 100 units in capital, whatever the amount that this investors invested in one of the two assets, right? So one of the assets is going to give a payoff of 64 with a probability of half, and a payoff of 225 with a probability of half if 100 unit is invested in that asset. And the other one gives a payoff of 0 with probability 3/4, and a payoff of 1024 with probability 1/4, right? So if you compare these two things, you will notice that the second asset has a much higher spread, right? In particular, there is a 3/4 chance that all money will be lost. But then again, there is a 1/4 chance that money would be multiplied more than 10 times, right? Instead, in asset one, the spread is much lower. So there is a possibility of loss that the 100 can become 64. But there is also a possibility of gains, so that the 100 becomes 225. And the possibility of the gain and the losses are more equal here compared to the second case, right? And of course, the loss, if it happens, is not so low. And if the gain that happens is again not so high as the gain that would have happened, right? So this is the situation, and the manager has to basically decide where should he place the money, right? So here we are assuming that the manager is going to act in the self-interest of the investors, and so therefore would try to maximize the expected utility of the investors. And this is the situation. Okay. So first question is that in the absence of any government intervention and so on, what is the lottery that would give the investor the highest expected utility? And would the investor have been better off by putting money in one of these two assets, right? So notice here, we are not looking at the combination possibility of putting amount of money in different combinations in different assets that will come up later. Here, the choice is put money in asset one or put money on asset two, or the third choice is that you don't put money in any of these assets and just consume that whole amount of money just on your own, right? So which is better among these three choices? That's the first question. So we can answer this by looking at the expected utility of the lottery in the different cases. So if, for instance, the money was put in asset one, so then we have to look at what's the expected utility of lottery in asset one. So with probability half, this 100 units of money will become 64, and with probability half, this 100 units will become 225. So this is the expected utility of the lottery, right? Half of square root of 64 plus half of square root of 225. Again, how do we get this? We are basically using this expected utility form to evaluate this, right? And so if you do the calculation, this turns out to be 11.5, right? What happens if money was put in lottery 2? So then you have got with 3/4 probability, this becomes 0. And with 1/4 probability, this becomes 1024. So again, you can put this in the expected utility form and you can calculate and show that this is 8, right? So if there was a choice of putting in money in lottery 1 versus lottery 2, then clearly from the investor's perspective, they would be much happier if you put the money in lottery 1, right? Or on asset 1. Okay, and remember, there was this choice of not doing anything with the money, but just kind of keeping this money instead of putting it in any asset. So what that would have implied is that the investors would have got 100 in each state of the world. And if you then do the calculation here based on this expected utility, that would translate into an expected utility of 10, right? So now we can compare these three numbers, 11.5, 8, and 10, and we can clearly see that 11.5 is the highest. So therefore, the money should have been put in asset 1. Okay, now imagine that the government is concerned that you have got investors who are losing money, right? So in the first asset, this 100 unit can become 64, and in the second case, this 100 can become 0. So in each case, you have got investors losing money, and basically they come up with an insurance scheme that is going to reimburse investors for any loss they occur, but not all the losses, right? So the maximum amount of reimbursement that's going to happen is 36. So if this is the policy and this policy is available to all the investors, then what are the expected utility that these investors now receive in each lottery? And under this case, which lottery should the manager choose? And finally, are the investors better off or worse off with this insurance scheme? So if we now do all the calculations, so we need to think about what are going to be the payoffs in the different states, right? So let's first consider lottery 1. So remember here, without the government insurance, the payoff was that with probability half, you are going to get a payoff of 64, and with probability half, you are going to get a payoff of 225. Now, what happens is that because of the insurance, that the government is going to reimburse you to up to 36 units if they suffer a loss. So this 64 is an example of a loss, right? Because you started out with 100 and you end up with 64. So in this case, the government is going to give you 36 units more. So you basically end up with 100 in this state. So you have now basically 100 with probability half. And in this case, you still have 225 with probability half. Why do you have 225? Because this is not a case of loss, right? You had 100 to start with and you end up with 225. So under this scheme, the expected utility of lottery 1 is half of square root of 100 plus half of square root of 225. And if you do the calculations, this is equal to an expected utility of 12.5. What about the second asset? So again, if the payoff is 1024, there is no loss, so the government does not pay you anything. But if the payoff is 0, then the government pays you, but only pays you 36, right? Remember, which is the maximum amount of reimbursement, right? So therefore, the expected utility in this case is going to be 1/4 of square root of 1024 plus 3/4 of square root of 36. Again, if you do the calculation, it's 12.5, right? So now we can see that as a result of this government intervention, basically the expected utility of the two lotteries are the same now, right? This is different from what we had before, where the expected utility of lottery 1 was actually higher, strictly higher than the expected utility of lottery 2, right? So now basically the manager is indifferent between these two things, right? This is still better than not putting the money in any of the assets, which is what you would have got as 10. And are the investors better off compared to before? The answer is yes, right? How do we see that? Because earlier the maximum expected utility that they had was 11.5. Now the maximum expected utility that they have is 12.5, right? So the investors are clearly better off with this insurance policy. Now, so far, this is insurance for free, but somehow this money has to be also funded. And so therefore, now the government thinks of asking the investors to pay a premium, right? In both cases, first, we are asked to calculate what's the actually fair premium that the government should ask for. And then suppose that the investors had to pay this premium, then which lottery would they choose, right? Okay, so The thing to note is that firstly, the actually fair premium might be different for these two different cases, right? So you have to actually calculate that and see if they're what are the numbers that we come up with. So that's the first step. So what is actually fair premium? So from the insurance company's perspective, an actually fair premium is the one under which, in expectation, they make zero profit, right? So this is the basic definition that you have to work with. And so now if you put all the information together, so suppose in the first lottery, they had decided for a premium of P, right? So let's now think about it. So this premium P is going to be collected regardless of state one happens or state two happens. And what is the payout that the government insurance company, if you like, has to give? So it will only pay out in the case where the lottery gives a payoff of 64, right? And in this case, the payout is exactly 36, right? Which is the maximum amount. So therefore, if we were to calculate the actually fair premium, so for the first lottery, this is going to be the equation, right? So the government is going to get P in each state, but has to pay out 36 in one of the states, which happens with probability half. And so therefore, the expected profit from this lottery for the government is half of P plus half of P. The premium P has to be paid regardless of the state. And with probability half, it has to pay out 36. So therefore, the expected cost is 18. And so therefore, the actually fair premium is such that P is equal to 18 for the first lottery. What about the second lottery? Well, in this case, the payout only happens in the state where the payoff becomes zero for the investors. So that happens with probability 3/4. And in that case, the payout is 36, right? And again, with 1/4, the payout is zero. So you can use this information. So in this case, the government's expected profit is going to be P, which is the premium, minus 3/4 of 36. So therefore, the actually fair premium is 27, right? Notice that for the two lotteries, the actually fair premium is actually different, right? Okay. Now, suppose the investors have to pay this premium, right? So what is the expected utility? So here, let's think about it. In the first case, where the money becomes 64, the government will pay out, right? Will pay out an amount equal to 36, but they also have to pay this premium, right? Which we calculated to be 18 in this case. So this premium 18 has to be paid in the both states. And so therefore, in one state, they end up with 100 minus 18. So this is again 64, which is the amount that the asset is worth, plus 36, which is the insurance payout, minus 18, which is the premium, right? So that is where we get 100 minus 18. And in the other state, there is no payout, but this premium 18 has to be paid, right? So you end up with getting 225 minus 18. So this is where we can put in the numbers. And so therefore you can calculate and show that this is 11.72. What about the second case? Well, you can do the same calculations. So in one case where the payoff becomes 1024, there is no payout. So therefore, then only the premium has to be paid. So therefore, this is the total amount that the investors are going to have. In the second case, when the payoff becomes zero, then the insurance payout happens. But again, now the premium has to be paid. So this is the expected, this is the amount that they're going to get. And you can use that to calculate the expected payout. And so therefore, now if we compare again, we get that in the first case, the expected utility is 11.72. In the second asset, the expected utility becomes 10.14, and therefore the first utility offers a higher expected utility, right? So this is a situation where, again, it was slightly different. Hopefully now you also understand a bit better about how to calculate this actually fair premium. And we can see what is basically the effect of offering insurance and how that actually affects the different choices that people have in terms of whether you are asked to pay the premium or not, or whether how much insurance you're getting, and so on, right? So these all affect the choices that you have.